This is lecture 7 of the course on galaxies. So one principle from physics, from statistical mechanics that we use extensively in galaxy evolution is the ergodic principle. So suppose I ask you to figure out how planes take off at a particular airport, right? Not what you normally do is maybe make a video of a single plane taking off and then tell me, okay, there it goes like this and turns and then takes off. Occasionally you will have a traffic jam like this of planes, and instead of taking a video, which means something over a period of time, you can take a single snapshot and figure out how planes take off at this airport, because you can see them moving forward, and then there is one aircraft taking off to the right over here. So you can immediately get a full picture of what's going on. When we study galaxies, we do exactly this. We cannot afford to wait for the galaxies to evolve, because they evolve on time scale of 100 million years or more. Since we can't afford to wait that long to see a single galaxy evolving over time, what we do is, instead of doing a sort of time averaging, we do ensemble averaging, which means we observe a large number of galaxies at in one go by, for example, looking at that Hubble Ultra Deep Field kind of thing. We observe thousands of galaxies in one shot, and then we try to see whether from that we can build up a picture like this of how galaxies are changing from one type to another, or how they are gaining stellar mass, how AGN feedback is working in them, or whatever questions you want to answer about galaxy evolution is done with single images, single epoch images, under the assumption that the ergodic principle holds. So if the time average and the ensemble average are not equivalent, then everything that we are doing goes for a complete toss. But there are reasons to believe that this is a very good assumption and it works, because there is no evidence that has come forward that indicates that this is not true. But there are no inconsistencies in the picture. So in order to study galaxy evolution via large-scale structure surveys, so we've looked at large-scale structures so far just based on how galaxies are distributed on the sky. But if you want to use those surveys for galaxy evolution, what is typically done is what is shown here. You do wide area surveys like SDSS main, which surveys the nearby universe. Then you do SDSS luminous red galaxy sample to study evolution of a subsample of galaxies, but at larger redshifts. And then what you can also do is carry out very deep surveys going out to redshift of 1 or so with instruments. So for example, here I've shown you examples of 2 fields that have been observed as part of a survey called VIPERS, which has been carried out using a spectrograph on the VLT telescopes. And it basically reaches out and allows you to map the large scale structure out to redshifts of about 1 or just over 1. Remember here that you must do multiple fields, because the moment you restrict yourself to a small cone, a small angle, solid angle on the sky, you are subject to cosmic variance effects. So in order to mitigate that, they say that, okay, we will observe in several different directions. So VIPERS, for example, has done W1, W2, W3, W4, and so on, observed in many different directions and mapped the large scale structure in each of those directions. And so if you want to get the average properties of the large scale structure, you can then average the properties over different lines of sight or different directions in the sky, so that your cosmic variance, which is an effect basically which states that if you look in some particular direction, if it is different from the sort of average, then you will be completely misled. So you need to look in several different directions. The probability of looking in special directions, if you look in 4 or 5 different directions, that all 4 or 5 are by chance all very special directions is small. So you will get a sort of average, you'll get the average properties right. Okay, so far we've talked about imaging and spectroscopic surveys with optical telescopes of galaxies, but there are also large area surveys that have been carried out at other wavelengths. In the X-ray, you had many years ago, about 40 years ago, the Rosat All Sky Survey. In the ultraviolet wavelengths, you had a satellite called GALEX, and that performed what is called a all sky imaging survey about 20 years ago. Again, around 25 years ago, or a little more, a near infrared survey was conducted. Of course, the X-ray, Rosat and GALEX were both space telescopes, but the TUMAS All Sky Survey in the near infrared band was conducted with 2 ground-based telescopes, one in the northern hemisphere, one in the southern hemisphere, so that the entire sky could be covered. At mid-infrared wavelengths, you had the WISE survey going from about 4 or 5 microns out to about 22 microns, covering the entire sky. In the far infrared, in the 1990s, you had a satellite called IRAS. 1980s, you had a satellite called IRAS, which again carried out all sky survey of the far infrared sky. And of course, the far infrared and sub-millimeter sky has been extensively observed with a slew of satellites designed to observe and study the cosmic microwave background. So you had COBE in the 1990s, and then a few years later you had WMAP, and then more recently you had the Planck satellite. All of these things, 3 satellites, are cosmic microwave background explorers, and they operate at wavelengths of just under a millimeter. So these are the kind of surveys that have been done, some of them for different purposes. So for example, when they did the cosmic microwave background survey, they surveyed the cosmic microwave background, but in the foreground was our whole Milky Way galaxy. And there were also other bright galaxies which appeared at those wavelengths. So they had to do foreground subtraction, careful modeling of the foreground and subtracting of the foreground in order to see the signal coming from the CMB photons. So if you use that data, you can use, so although it's a CMB survey, it can also be used for the study of our galaxy and other nearby galaxies, which has also been done. In the radio, one has had a slew of large area surveys. NVSS and FIRST were 2 1.4 gigahertz surveys that were done in the second half of the 1990s. And more recently, TGSS, the TIFA GMRT Sky Survey, was also a large area sky survey. Neither of these are all sky, but they cover whatever can be seen from the particular telescope location. So TGSS, for example, I think is about nearly 3/4 of the sky that is accessible to the GMRT. Okay, so these are all large area surveys, which means they cover at least a third or 1/4 of the sky and at a particular wave band. Some of them are done from the ground, some of them are done from space-based telescopes, depending on which location is more suitable for a particular wave band. In addition to this, there have been with many other telescopes, and also in some cases with these telescopes, like GALEX, for example, was used for all sky imaging survey, but it was also used for observing specific objects with higher sensitivity. So that would be a pencil beam survey with GALEX. Have been done. So these kind of surveys have been done not only with these telescopes, but with other telescopes as well. So for example, narrow field telescopes, narrow field of view telescopes like Hubble or JWST or Herschel and so on, they can only be used for, they can't be used for large area surveys. It would take too long. They're used for pencil beam observations, pencil beam surveys, and they've been used extensively, and these surveys are numerous. All of these are less useful than surveys involving optical spectroscopy. And any idea why that may be? So remember, these are all imaging surveys in different bands. Output is images, not spectra in general. But optical spectroscopy is very critical in studies of galaxies. Why? You can infer the composition. Yes, that's important. Huh? Yeah, you can have absorption lines, emission lines, etc., and you can use them to study the chemical compositions of these galaxies. But far more fundamental than that, redshift. Yes. So in all of these imaging surveys, it turns out that except for certain narrow bands, for example, in the mid-infrared or in the millimeter, many of these surveys or imaging surveys are bereft of any lines. So for example, in the radio, except for the H1 line, the OH line, one or two lines like that, there are no lines. And therefore, if you observe galaxies, you will get continuum emission from them. You'll see how bright they are at radio wavelengths, etc. But you will never be able to figure out how far that object is. So last time I showed you a plot, an all-sky plot with millions of NVSS sources. So we know how bright those sources are in terms of flux. But for most of them, we don't know how far they are, and therefore we don't know how luminous they are. We don't know how to convert flux into luminosity. And luminosity is obviously the physical quantity that is of interest. Flux doesn't tell you much because it changes depending on how far you are from the object you're studying. So that is why optical spectroscopy is so critical, because it allows you to get a redshift and allows you to determine distances and use that to convert fluxes into. Okay, another simple question. Why have we so far ignored radio and X-ray observations of galaxies so far? And we will continue to ignore it more or less for much of the course. Sorry? Yes, they're not very bright. So, but what kind of galaxies? Non-active galaxies. That's correct. So in this course, you have a separate course to study active galaxies. I'm going to not talk much about active galaxies except in the context of galaxy evolution. So because these galaxies are invariably, at least at the bright end, X-ray and radio sources are invariably AGN, active galaxies. And since we are not studying active galaxies, we haven't focused much on radio and X-ray observations of galaxies. Okay. So now we've looked at, there exists large-scale structure. We've observed it. We have seen it. The question is, how do we quantify it? How do we measure it? And this is important because I told you last time that theories and numerical simulation of galaxy formation or structure formation, they make certain predictions about what is the scale of the structures that you should see at different redshifts. So in order to compare what the simulations tell you with what is actually observed, you must measure quantitatively the structure in some way. And the most common way of doing that is using the 2-point autocorrelation function. The word auto here refers to objects of the same type. Later on, we'll look at cross correlation functions. wherein you have objects of two different types. So you can define a function xi r, and you define it as an excess probability of finding another galaxy at a distance r from some galaxy relative to a uniform random distribution, right? So if the universe is not clustered in any way at all on any scale, then the xi of r would be 0 at all, would have a value of 0 everywhere. So it's the excess probability above random. There's no excess probability of random. The universe is random. But of course, we know that the universe is clustered on small scales. For small values of r, one can use a power law with of this form, r over r naught greater than raised to the minus gamma. And the best fit r naught is about 5 H inverse megaparsec, and gamma is 1.8. Okay. Obviously, gamma and r naught are functions of various galaxy properties. For example, as we shall see later, there are differences in the clustering properties of ellipticals and spirals. There are differences in the clustering properties of low mass galaxies and high mass galaxies, and so on. Okay. So they depend on the galaxy properties. Clustering in clusters is stronger, and the slope also is not constant. If you go above r over r naught of about 2, the slope begins to steepen. Okay, so the power law index and the r naught could both change so it's not a constant value throughout. As you go out, the slope changes and the r naught changes. Okay, so for small values of r naught of r, this is the measured autocorrelation function of galaxies from the 2DF galaxy redshift survey. And as you can see, seems to be a nice power law with deviations shown over here. Power law appears as a straight line if you plot it as a log-log plot, which is exactly what's done here. Nice power law with that slope. So question is, can the 2-point autocorrelation function have a negative value? Yes, when? Okay, so where will you expect to have that? Voids. So if you're looking at voids in the universe, then you have one galaxy in a void, you expect to find another galaxy at a certain distance, but because it's a void, there are fewer galaxies than the average, right? So you have to go a larger distance before you find a galaxy. And so the density of galaxies here in the void is less than the average density. So there is no excess probability, there is a lowered probability deficit of galaxies. And yes, so the 2-point correlation function can have a negative value in voids. R0 indicates it's just a scaling for the power law. Okay, you fit it. It is giving a no. See, suppose you have a scaling index. Okay, so see, this R is not absolute. So you may have two situations where the best fit R naught and the best fit slope gamma are different, and that R naught is an absolute value. It scales it up and down, right? The function will go up and down depending on the value of R naught, and the gamma will change the slope. So the straight line needs 2 parameters to define it.
Sir?
Sorry?
Sir? Yeah, so how we will get the R naught?
How will you get the R naught?
Yeah.
You will get the R naught by fitting it as a function of R.
Like suppose this plot, where is the
Yes.
R naught?
Yeah.
Where is the R naught here? Is it,
R
is
naught
it
is the absolute scaling, because if the R naught is different, okay, you will get a different at R equal to R naught. Okay, you will get the constant value irrespective of R naught.
this is
But at
log log?
half R naught or 2 R naught, you will get different values depending on the slope and the value of R naught. Yes. So this is only for galaxies that are so it'll, as we'll realize later on in the talk, if you only consider clustering on small scales, if you only say I'll only go up to 1 megaparsec or 2 megaparsec or 3 megaparsec, you'll always find excess clustering except in voids, right? And it turns out that most galaxies, I mean, by definition, most galaxies don't lie in voids. So if you take an average over all galaxies, there is a overdensity on small scales, always. On large scales, you can have an overall underdensity. Okay, so how do you estimate this psi of r? What do you do? What you could do is you count the number of data pairs, TD, and the equivalent number in a randomly generated Poissonian catalog. Okay, so for example, you have your data catalog wherein you take one galaxy and you measure how many galaxies are there at a distance of 1 megaparsec, 2 megaparsec, 3 megaparsec, integrated over theta and phi, but also averaged over all galaxies, because no one galaxy is special. So you do that with every galaxy. You find what is the number of galaxies at different distances, at different R's from it, and the equivalent number in a randomly generated Poissonian catalog. So you construct another catalog, which is a mock catalog, a dummy catalog, artificially constructed catalog, which has galaxies having the overall same number. So suppose you're looking at a volume of, let's say, 5 megaparsec by 5 megaparsec by 5 megaparsec cube, right? You construct a mock catalog which has the same overall density of galaxies per unit volume, but does not have any clustering. They're just random. X, Y, Z coordinates are completely random. If you do that, you get a random catalog. And within the random catalog, you carry out the same exercise. Take every galaxy, measure how many galaxies are at 1 megaparsec, 2 megaparsec, 3 megaparsec, etc. Average over all galaxies, and take the ratio of DD over RR. Now, if your DD is also a random catalog, average of DD will be same as average of RR, and you'll get 1 here, 1 minus 1 will be 0. So no correlation. No 2-point autocorrelation. Function is 0 at all R's, but in general, it won't be 0, and you'll be able to measure the autocorrelation function. Now, it turns out that when you have a box with edges, small box with edges, then you may have galaxies outside the box, but because you are near the edge, you're not able to count them, right? They're outside. But so near the edge, all kinds of edge effects come into the picture, and that can damage your measurement of psi r. So Landy and Zale in 1993 wrote a paper in which they showed that instead of using this kind of estimator, if you use this kind of estimator, then you have a much better measure of the autocorrelation function. So here's the formula. So you do DD exactly like you did here. You do RR exactly like you did there. But here you do another measurement. This RD measurement is that you take the number of data random pairs. So what you do is you take one galaxy from the data and find the distance from this galaxy, not by using the other data galaxies, but using only the random galaxies. So it's a cross correlation between your actual data and the randomized data that you've constructed. And just multiply that by 2 and divide by RR, and that gives you the measure of psi of R. So in this paper, Lundy and Zale, the whole paper goes on to explain why this is a better measure, and where edge effects are not a consideration. This gives measurements that are equivalent to this measurement. And even when edge effects are there, this one does a better job of not being affected by the edge. You can also measure psi of R by dividing your whole volume into small cells, small cubes, and measuring the overdensity. So suppose you say that, okay, I have a big box which is 10 megaparsec by 10 megaparsec by 10 megaparsec, but I'm just going to take cubes of 1 megaparsec everywhere, and I'm going to count in each cube what is the overdensity with respect to the average. Okay, so I'll get, as a function of some arbitrary starting point, I will get this excess. Then you can compute the value of psi of R as the expectation values of any pairs of objects x1 and x2. So you construct like a density field with this, and then you do you multiply an average, find out the expectation value of the overdensity field to get a measurement of psi x1, x2. Okay, but so whatever technique you decide to use, I've shown you 2 ways of measuring psi of R. There are in the literature 3-4 other methods that people have suggested. We won't go into those. But whatever method you choose, the results that you get are consistent with each other. So what is shown here is the are bright galaxies more clustered than faint ones? So this is the question that we want to answer by looking at this function. So are they more clustered or not? This is corrected for. These are all volume limited samples. Nearby galaxies, you don't have to worry too much about the Hopkins bias. So what does this figure tell you? Are they more clustered or less clustered? Bright galaxies. Y-axis is the psi of R, the autocorrelation function. Bright ones are more clustered. And how do you know that? Correct. Yes. So psi of R at whatever R you choose in this figure, the red curve is above the other curves, right? And therefore, yes, bright galaxies are more clustered than faint ones. Okay. Are red galaxies more clustered than blue ones? Huh? Up to a certain value. So up to about, say, 10 megaparsec, H inverse megaparsec, these galaxies are more clustered because the red curve, which represents red galaxies, that is above the others. Beyond that, red is somewhat less clustered, than the others, but the error bars are large. So we can't say anything for sure, but definitely at distances less than 10 H inverse megaparsec, red galaxies are more clustered than blue ones. We'll come to that. A lot of the course is devoted to that. So just like you have the 2-point autocorrelation function, you can define what's called a 2-point cross correlation function, in which we correlate two populations, which are essentially independent objects, but there are reason to believe that they may be clustered. So you can ask the question, are galaxies clustered around quasars? Right? And then you can then construct the cross correlation function by taking one object of one class, let's say take one galaxy, and find out the distance from that galaxy, how many quasars are within 1 megaparsec, 2 megaparsec, 3 megaparsec, etc., and construct that cross correlation function and repeat this exercise for all galaxies, and you will get an average over them, and you will get the cross correlation function between galaxies and quasars. So do you feel there will be some clustering like this? Yes. Okay. So I'm not going to show the cross correlation function here, but yes, galaxies are clustered around quasars. There is if you take any quasar, will be an excess of galaxies around. Correct. And that is very often AGN. Okay? At high redshift, it becomes, at low redshift, it is more likely to be radio galaxy. At high redshift, it may be a quasar. And because of how hierarchical galaxy formation happens, it turns out that galaxies and quasars are clustered. So galaxies are clustered around quasars. So you can also do 3-point autocorrelation function. So this, of course, is less commonly used, but now you, instead of doing one, that you find the excess probability of given one object, what is the excess probability of finding object of at a certain distance and finding another object within that distance. Okay, so there are 3 points. What is the clustering probability of not of 2 galaxies but of 3 galaxies or 4 galaxies? That can also be computed. Very often, because spectroscopic surveys are very expensive and photometric surveys are cheap in terms of cost and telescope time, one cannot do spectroscopy of all the galaxies. But one can easily measure angular separation between galaxies. So if only 2D information is available, then you can compute the angular autocorrelation function of galaxies. Again, it turns out that that's some power law with some index. If all galaxies are at the same distance, it can be shown that this index beta is nothing but gamma minus 1. So, for example, if you're measuring the autocorrelation function in galaxies and in a galaxy cluster, where you don't know the distance to the cluster for some reason, but you know that all galaxies belong to the same cluster. How you would do that is very difficult, but without measuring it, then you can compute the angular correlation function, autocorrelation function, and use that to compute gamma. Gamma is more physical. Okay, this is very, very tricky to interpret, the angular correlation function. So it is used only in situations where absolutely nothing else can be done. You're at the faintest end of your observation, no possibility of getting a spectrum, etc., etc. Then you use the angular autocorrelation function. Otherwise, you use the regular spatial autocorrelation function where R actually specifies a real distance in space. So these are the various correlation functions that we've looked at: 2-point autocorrelation function and 2-point cross correlation function. These ones are used in the literature all the time, left, right, and center. The 2-point angular autocorrelation function, as I said, is less useful, sometimes used. 3-point correlation function is useful, but is also not very commonly used. Okay. So suppose we measure the autocorrelation function over all kinds of length scales. What will we be able to probe? What we will be able to probe is basically how density fluctuations have grown into clustered structures at different length scales. So on the x-axis, you have scale, millions of light years. And we are trying to find out what is the clustering on very, very large scales as well as on very, very small scales. So you can see here, you're going all the way from like 1 million light year to 10⁵ billion light years, so 100 billion light years. So on the largest physical scales, the most effective probes come from measurements of the cosmic microwave background and seeing whether on very large separations, because remember, these are the only real all-sky surveys of uniform sensitivity, whether there is any excess density at those large scales. And there you can see that yes, there is, but the slope has steepened, it continuously steepens, and the excess probability is not very high. There is some excess probability, but it is extremely small. Cluster abundance. So there are predictions of all models of galaxy formation, which tell you quite reliably, or claim to tell you quite reliably, how many clusters should form at any given point in time. So if you're looking at the local universe, there are predictions available on how many clusters you should see. And the cluster abundance is basically just a way of finding out how many clusters are there, cluster density, number of clusters per unit volume at different redshifts, and how that matches up with the predictions from the theory and the simulations. So very often X-ray, very often clusters emit strongly in the X-ray. So the X-ray telescopes are often used to study these objects. You can even use submillimeter telescopes because of the Sunyaev-Zeldovich effect, where the CMB photons that are coming from the background, once they encounter this X-ray photon-rich cluster, then the CMB photons get scattered, and they come into the millimeter band, and you can see them as bright patches, bright millimeter sources or sub-millimeter sources with these telescopes. Yeah. What do you mean by mean density? Yes, so I don't remember the exact value, but it's obviously very small, right? Yes, no, this is not the scale of particles. Remember, this is number density of galaxies, which you can measure. So in the local group, for example, within a megaparsec, we have one more galaxy, right? So if you take a megaparsec cube centered on Milky Way, you'll have Milky Way and Andromeda and some dwarfs. So you'll have a number like 30. And that is overdense by, I think, maybe a factor of 5 or 10. So what I'm saying is compared to the average density, this is about, because we are in a group, we are not in the field, we are in a group, the over density is probably factor of 10 larger. So if you want a rough number, I would say one galaxy per megaparsec cube, including when you include dwarfs as well. Yes. No, that is just measuring on that angular scale or on that distance scale, how many excess galaxies are there. And they're there, but they're very few. So what you do is on the CMB, you take one galaxy here, one galaxy there, which means two vectors separated by large distances. And you know what distance that corresponds to now, right? Because the CMB is filling up your whole sky. You then compute because see, when you do these measurements to the CMB, you're seeing the universe when it was really very small. Okay, so these are those lengths as seen today. So you don't actually see those lengths, you're seeing them as they were in the past. So you don't actually measure actual galaxies between at those 100 billion light years. What you do is you measure temperature fluctuations in the cosmic microwave background at large angular scales. So we'll come to that. In fact, when we start talking about the power spectrum of galaxies, you'll understand that this is a measurement of the power spectrum on large angular scales, okay, or small values of the wave number and so on. Yeah. Okay, so there we have the power spectrum coming in. So you can define the overdensity field everywhere in the universe as delta x is as nx over n minus 1, right? So nx is the number of galaxies in that delta element, volume element, and divided by the average density of galaxies in the universe. Subtract 1 to get the overdensity. So once you have this delta xs defined everywhere, then you can define the following two Fourier pairs. You have a delta x, okay, and you have its Fourier transform delta k. Then of course Fourier pairs, and you can define where k is the wave number. So when x is large, okay, say gigaparsec, k is small. And that is what you're measuring in the cosmic microwave background. Small values of k are what are measured. The power spectrum is defined as pk mod of delta k square. This is just the definition of the power spectrum. And if the 2-point correlation function is the expectation of the overdensity field, which is the definition of a 2-point autocorrelation, then the power spectrum is the Fourier pair of it. And these two are equivalent to each other. By measuring the power spectrum, you can calculate the 2-point autocorrelation function, or if you measure the autocorrelation function, you can compute the power spectrum by taking Fourier transforms. So this is a plot that shows both. So this is from the Las Campanas redshift survey, wherein you have the correlation function on the left, right? And you have the power spectrum on the right. Correlation function is something that we can physically measure quite easily via observations in large surveys, but we need the power spectrum to compare with theory. The theory gives you a power spectrum typically, and so you have to take the Fourier transforms and so on. Of course, you have to worry, these are discrete Fourier transforms. While taking Fourier transforms, you have to worry about all kinds of effects that plague the Fourier transform. But if you do it right, you can compare with the K values, which are per megaparsec units. Remember, everything here has to be done in terms of co-moving H inverse megaparsec. The co-moving part is important. So if you're comparing volume densities at redshift 0.1 to 0.2, because your sample spans that redshift, you have to convert the volume to a co-moving volume. You have to take into account the fact that the universe is expanding. So the scale factor of the universe should go into your calculations. Right. Yeah. Sudden discontinuity. Yeah, no, I also noticed it just now. I don't know. I will look it up and I will tell you next time why there is a sudden discontinuity here. So probably they're not hitting that K at all. That is the likely reason. So I don't know what this is. I'll find out and tell you the next time. So clearly, I think here the power spectrum is only covering this part. You can check because it'll be the inverse. So the largest value here is about 10, 11, 12 megaparsec. Okay. And if you go here, which is K inverse, if you go to 12 megaparsec, that's here. So I think they have indeed gone here. So let me check and confirm. Okay. So this is an important plot from a paper by Max Tegmark and collaborators in 2004 that shows the power spectrum. Okay. No, there is R, but there is a 2 pi factor over here. So we have to take that into account. So they may not actually go beyond this. Okay. So the K number and the wavelength are not just reciprocals of each other. There's a factor of 2 pi, which you have to take into account. Okay. Right. So on the largest angular scales or small values of the wave number K, we measure, as we said, on using the cosmic microwave background. Then cluster abundance and so on. SDSS galaxies contribute to this part of the power spectrum. And then once you go to power spectrum on large wave number or small length scales, then you are looking at initially weak lensing. Okay, and we'll come to weak lensing and how weak lensing is used for studies of large scale structure a bit later. And then you have the Lyman alpha forest. So the Lyman alpha forest is a very, very critical measure of the large scale structure because of one important advantage that it has. When you look at absorption lines, it doesn't, signal to noise doesn't depend on how far the absorber is from you. Okay, once so many % of the light is absorbed, that much % of the light is absorbed. So if the percentage absorption is large, even if the absorber is far away, you still get a good signal to noise ratio, provided of course that the background quasar or whatever it is that is being used to illuminate the Lyman alpha forest is bright. Okay, so we haven't yet told you what Lyman alpha forest is. So do you guys know what that is? Yes, so it is basically all the hydrogen clouds that lie between us and some distant emitter like a quasar. Each of them absorbs the Lyman alpha photons, and they absorb when they see a Lyman alpha when they see a photon with a rest wavelength corresponding to the Lyman alpha wavelength, it absorbs it. So it gets redshifted differentially. The Lyman alpha line itself is redshifted. And since these other objects are closer to us, blueward of the Lyman alpha emission line, you will see absorption from all the absorbers that are lying along the line of sight. So we'll come to that bit later. Okay. So by measuring using the Lyman alpha forest, weak lensing, cluster abundance, the SDSS survey, and the cosmic microwave background, all of these measures together give you a measurement of the correlation function or the power spectrum on scales that span about, say, 10,000 in wavelength or K number, dynamic range of 10,000. On lens scales that go from 1 to 10,000 or angular scales that go from 10,000 to 1, you are able to measure the power spectrum. And what is shown with this sort of blue continuous curve is the best fit theoretical power spectrum. And this corresponds to the cold dark matter power spectrum. The power spectrum of warm dark matter looks different. On which scales? Small scales or large scales?
Small scales.
Small scales, yes. So it is these measurements which are on small length scales, okay, which are very crucial in separating the prediction of warm dark matter and cold dark matter. And it was only with the advent of surveys such as Sloan and dedicated Lyman alpha absorber studies that it became possible to measure the power spectrum on these scales and therefore differentiate between CDM and warm dark matter. And it was around this time, I mean, this is from a review paper by Techmark. So over the years previous to that, 10 years or so previous to that, it became well established that we live in a CDM universe. And this, if you want it summarized in one plot, then that's it. Yeah. So now there is another effect known as the baryon acoustic oscillations. So you know that in what we are seeing as the cosmic microwave background is essentially the primordial plasma. Okay, and just like you have acoustic waves in a plasma like the sun, you had acoustic waves that were present in those in that ancient plasma after the Big Bang. Now, what happens is that that plasma had basically two or three different kinds of forces. One force was the repulsive because of the high temperature, the expansion of the baryons itself, which produced some kind of outward pressure. Then because of the photons, which were getting constantly absorbed, there was a photon pressure, radiation pressure that was there acting outwards. And that was being counteracted at some level by the gravity. That gravity, of course, came from the baryons themselves and, of course, the dark matter at that time. So, but there was a time came after some time wherein there was this matter radiation decoupling and the photons started free streaming through the universe. Once photons were not getting constantly absorbed and re-emitted, the photon pressure that was there, that dropped drastically. The photons were streaming freely through the universe. The atoms had begun to form because protons and electrons were coming together. And so there was this baryonic pressure which was still there, but the photon radiation pressure went down. And at that point, what happened was the acoustic waves that were there in the plasma got frozen on some length scale. And then that length scale increased. As the universe expanded, that length became longer and longer and longer. So any kind of acoustic wave frozen in the power spectrum of that primordial plasma would correspond to an overdensity at the present time. Because what happened was that overdensity remained, and around that overdensity, matter began to coalesce and its density began to increase. So now you can ask the question, on what length scales should you see an increase in the autocorrelation function of galaxies if it corresponds to those baryon acoustic oscillations from that early time? So, of course, this will require you to know the cosmological parameters. What is the value of H naught? What is omega naught, omega lambda, etc. Correct? But if you make some assumptions about these values, you can predict on what scales you would expect to see the baryon acoustic oscillations imprinted on the structure of clustering of galaxies. So people did this rough calculation with the known values of the cosmological parameters at that time. And they said that somewhere around 100 H inverse megaparsec, you should see that signal. Somewhere around that, because we didn't know the cosmological parameters exactly. So this is a measure of the, basically it's an indirect measure of the angular, what's known as the angular diameter distance in cosmology. Okay, how does angular diameter change as a function of redshift? Right. So distance measured in such a way that the angular diameter theta is simply the size of the object that you're measuring divided by the distance, angular diameter distance to that object is your angular, the angular diameter distance is defined in such a way. Because of the decoupling between matter and radiation. That's the reason, because that equilibrium got broken. It was no longer see, the early plasma was acoustic waves were forming, they were getting destroyed, they were ebbing. So just like on the sun, the acoustic waves on different scales were there on different length scales. What happened was one preferred length scale got frozen in time. So there can be other acoustic oscillations also. This first peak, just like in the CMB, you have the first peak, second peak, and so on. This corresponds to the highest acoustic peak, what is being measured here. Others are too small to measure. So it is for the same reason that you see the acoustic peaks in the CMB. That's also because it's frozen. Whichever direction you look, it is on those length scales that there is an overdensity. Similarly, on certain length scale, 100 H inverse megaparsec, you should see a overdensity of galaxies. And this is what is shown here. Okay, so this is the, I think those curves correspond to three different models or measurements. I don't know. I think they correspond to different models, different values of the cosmological parameters. And you can see that the autocorrelation function falls and then goes up and falls down again. And this happens at about 100 H inverse megaparsec. We know the H value is about 70 kilometers, whatever. So 0.7 now, H100 is 0.7. So that divided by 0.7 will give you about 150. So on the length scales of 150 megaparsec, there is a slight increase in the probability of finding a galaxy. If you take any galaxy and you look exactly 150 megaparsecs away, this is a very large scale, not that clusters are too small for it, anything. You measure galaxies at that distance and you measure what is the random probability. and or what is the actual baseline probability. It may not be 0 here. It's very close to 0. May not be exactly 0. And here suddenly on those length scales, there is an overdensity and then it falls. So this was a discovery made by Eisenstein and collaborators with the Sloan Digital Sky Survey, which was the first survey which had that much fidelity to make this measurement. Okay, in order to make this measurement, you have to ensure that the error bars that you have on the computation of the power spectrum or the 2-point correlation function are very small. If they're not small enough, then you'll miss this blip because it's a very tiny blip. It's a very weak change. Okay. Yeah. One more thing to remember is that there is, I said that the angular correlation function and the power spectrum are exactly equivalent. They're not, because the power spectrum only worries about the amplitude. So what has been done here is that you have this image, okay, and which is of course real data. You take the Fourier transform, you will get an amplitude and a phase for this image. You get two two-dimensional images you will get, one representing the amplitude and one representing the phase. If you take the inverse Fourier transform, you should get back the same image. But if you do some trick, which is you take the amplitude, you take the Fourier transform initially, you take the amplitude, you leave it unchanged, but you take the phase and you randomize the phase. If you randomize the phase and then take the inverse Fourier transform, you get something like this. So obviously there is some structure in this, but you can't easily see the structure here. But if you take the power spectrum of this guy and this guy, the power spectrum is going to be identical because the amplitude has not changed, only the phase has changed. So power spectrum, since it does not care about or does not capture the phase information, that information is lost. But that is okay because you only compare power spectrum to power spectrum. But therefore, you may not get from the theory, if you try to construct an image and then compare that image with your observations, that is not going to work. Because these represent the same power spectrum, but obviously in the image space, they are looking very different. And that is why we go in only one direction always. The observers come, they measure the 2-point correlation function, and the theorists say, okay, give me the power spectrum. So you take the power spectrum and compare it with the theory, and then you check whether the theory works or not. So this is important to remember. Okay, I think I'll stop now because this is a slightly different topic about the cluster correlation function. So in cluster correlation function, how do you think this is different from the galaxy correlation function? Small number, yes, but the definition itself is different. What you do is, instead of asking the question, given a galaxy, what is the excess probability of finding a galaxy at a certain distance? You ask a question, given a cluster, what is the excess probability of finding another cluster at a certain distance? Right. So, so we'll stop here, and I will take any questions from here or on the Zoom.
Hello.
Yes, go ahead.
So can you go to the previous image?
Which one?
One more. Yes, sir. So,
Yeah.
here, can it be that the curves that are in different colors
Yes.
correspond to different values of redshifts? Because when we change the redshift, it means we are looking back. I mean, we are looking back in time. So over densities that are at present time may be stretched out due to the expansion of universe, while in past they might be more compressed, so peak might be greater for that cases.
Yes,
So
that is correct. But remember, then you should have separate data points at different redshifts also. Okay, you can't directly compare because the clustering itself has changed, right? So you should not compare the autocorrelation function on one scale with another scale at a different redshift. So you should make slices, and that is what they've done. So I don't think this corresponds therefore to this, because then there should be multiple. We have only one set of black data points. If there were multiple sets of black data points, then you could say that, okay, there is redshift evolution of the clustering, which is we are trying to measure. But I think I'll confirm this. Again, all of you can also confirm this. Just go to this paper, Eisenstein et al. 2005, and look at the caption for this figure. You will be able to figure out what this is. Yeah.
So,
Yes.
so will you put when will you put this lecture on the website?
The PDF I will put immediately. I actually have the recordings now of all the previous lectures. So maybe by tomorrow I will put up all the previous lectures, hopefully this one as well, the videos.
Okay.
But the slides will be put up immediately.
Hello, sir.
Yeah, go ahead.
So in the current power spectrum figure, when we use the CMB data points to probe the like 10 power 3, 10 power 4 megaparsec, the wavelength thing in the previous slide.
Yes.
So this is actually the current power spectrum. That is, we are probing the current power spectrum at 10 power 4 H inverse megaparsec. And we are
Yes.
using the CMB data to do.
Yes.
Okay.
So what we are doing, we are measuring the power spectrum, the angular power spectrum of the CMB photons. Now, one good thing we know is that all the CMB in every direction is at the same distance. Okay, exact same distance. So you can measure the 2-point angular correlation function of the CMB, and you can easily convert it. So you'll measure beta and you'll obtain gamma.
Okay.
I can, but not now. Maybe later. It's a little bit involved, but you can also, it's a standard proof. It's a textbook proof. You can just look it up. So this is what is used for the CMB. Because the CMB is at the same distance in whichever direction you look, you measure the 2-point angular correlation function and convert it to the 2-point spatial correlation function. And then, of course, the spatial scales are scaled by the scale factor of the universe. See, remember,
Right.
all of these are being measured at different redshift. The Lyman alpha forest may be at redshift 1. The SDSS galaxies are at very low redshift. Weak lensing is also at relatively low redshift. The cosmic microwave background is at very high redshift. So you have to take the scale factor of the universe, and remember the scale changes as A of t, right? So you know that the cosmic microwave background is coming from a redshift of 1100 or so. So the scale factor would have changed by 1 plus z factors. So these length scales are not real physical length scales. They're measured, they're the measured angular length scales on the CMB data converted to a physical scale now.
But sir, if we let us say we have no way of measuring that, but let us say at this particular time, we go to length scales of 10 power 4 megaparsec. We have no way of knowing that, but we'll find a similar power spectrum.
Yes, that is the expectation. Yes. You should find a similar power spectrum, but you have no technology to measure it. And the cosmology captures the full evolutionary history of the universe. Okay, so if your overall picture is correct, if the Big Bang model is correct, your dark energy parameters are correct, etc., etc., your supernova measurements are correct, you know exactly how the expansion history of the universe proceeded. And this curve takes all of that into account. That's why you don't have to actually make a measurement on length scales of 10⁻⁴ megaparsec of the correlation function to plot these 3 or 4 data points.
Right. Okay.
And you can see that one data point is not fitting the data, right? So this is not a perfect fit like you have for the Planck data. And that may be because there is some tension in the cosmological parameters, particularly the value of H0. There is what the Planck measurement shows and what the other measurements are showing is inconsistent at about 2 sigma. So maybe this curve is not right. Maybe it should go like that.